this is gonna be our last chapter. I've skipped some of the chapters for the interest of time. So it's gonna be on carbohydrates. Most of the food contain carbohydrates, including starch. The sugars that you eat in your bread, in your cake, in your cookies, those are starches and they fall under carbohydrates. So let's talk about this. What you see here, I think these are sugar crystals. Those are sugar crystals, contain disaccharides in it. Okay, they are very common in our lives. Common sugars such as sucrose, lactose, fructose, glucose are in your common daily lives. Those are carbohydrates. The name arises from the formula CnH2OM, and they are polyhydroxyaldehydes or polyhydroxyketones, which means you're gonna have OHs in the structures and an aldehyde, or you're gonna have OH in the structures and a ketone. Okay, so let's try and break down what you're talking about here. So carbohydrates can be classified into three. There is monosaccharide, which means you only have a single carbohydrate in there, or oligosaccharide, which means you have 2 to about 10 carbohydrates in the structure, or polysaccharides, you have more than 10 carbohydrates in the structure. You most likely have a polymer. I think one would even consider cellulose to be a polymer carbohydrate in this case. Okay. The poly and oligosaccharides can be broken down back to simple carbohydrates, what we call monosaccharides. Okay, so the single units are called saccharides. So if it's only one, then it's mono. If there are 2 to 10, it's oligo. If the saccharide units are many, it's poly. Okay, monosaccharides can further be classified into other classes. Triose, which means you have 3 carbons. Tetrose, which means you have 4 carbons. Pentose, which means you have 5 carbons. Hexose, you have 6 carbons, as in glucose. Okay. The structure of the carbonyl group also can be used to categorize the monosaccharide, whether you have an aldehyde or a ketone. So that's where you'll see the name aldose if you have an aldehyde, or ketose if you have a ketone. Okay, so triose. There are 2 forms of the trioses. You either have the aldehyde in the structure or a ketone. Like I said, if you have an aldehyde, it's an aldose. If you have a ketone, it's a ketose. Now, they are still trioses because you do have 3 carbons in the structure. Okay, see, you have 3 carbons all through. 1, 2, 3. For this one, there's no aldehyde, no ketone. So in this case, this is just glycerol. Remember, we used glycerol for polymerization. Okay, so that's just glycerol, but the trioses could either be an aldose or a ketose because you have 3 carbons. Okay, glyceraldehyde is the simplest aldose, and dihydroxyacetone is the simplest ketone. And during the biochemistry class, you'll talk about dihydroxyacetone as a byproduct, I think, of glycolysis. Both are related to glycerol by oxidation of a specific hydroxycarbon. So let's say you oxidize this part using PCC. You're gonna end up with an aldehyde. In the living systems, you will not use PCC, you'll use an enzyme. Okay, you'll use an enzyme, an oxidase. You'll learn this in biochemistry. I won't teach you biochemistry. You learn that in biochemistry. You use an oxidase to oxidize an alcohol to an aldehyde. Okay, alternatively, this middle one can be oxidized by PCC in the lab or using an oxidase enzyme. You convert the alcohol to a ketone. It's a ketone because we do have a carbon-carbon, so it's a ketose. So glycerol is considered the mother to ketose or the aldose. Just depends on which hydroxy group you're oxidizing. Okay. You do have longer than 3 carbons on the chain, so long aldoses and ketoses can be made by adding CHOH groups to the chain. So for example, if you add one more COH here, you get a 4 carbon structure. It becomes a tetrose. If you had from the first one, add one more COH, which is this part, you get a pentose. And this is how I'll be asking you to classify these structures as ketose, hexoses, and so forth. Treat tetrose, pentose, hexose, or aldoses or ketoses. Classification is a major testing point for this chapter and not memorizing how to draw. Okay. All right. So again, all these guys have aldehydes. Okay. You see the aldehyde functional group. So all of them are aldoses, which might have 4 carbons, 5 carbons, or 6 carbons. All these have the ketone functional group, so they are ketoses. And based on the number of carbons, they can be a tetrose, a pentose, or hexose. You kind of see that these could be drawn in Fischer projection. So we'll build up Fischer projection very soon, which is here. So you can draw the structures in Fischer projections. Okay. Fischer projections. We talked about Fischer projections and we assigned the RNS. But what I want you to remember is all the horizontal lines must be towards you. So if I was to assign chirality on the carbon containing 4 different groups, the stereogenic carbon, then I would say this will be priority 1, priority 2, obviously this is priority 4, this is priority 3. I gave this priority 2 because this carbon right here is considered to be bonded to 2 oxygens because of the double bond. This is only considered to bonded to 1 oxygen, so it's priority 2. This is priority 1 because the oxygen has high atomic number compared to the carbon, and hydrogen. So again, we consider 1, 2, 3. Right now we are going counterclockwise and S, but the smallest group is towards us. It needs to be away. The opposite of S turns out to be R. 2 chirality is R. So this is a glyceraldehyde, but it's an R-glyceraldehyde. Don't worry about the positive. That one usually comes by when you use your polarimeter. You'll find which direction it rotates the polarized light. But we did not do that, so don't worry about that. Don't worry about the 25, the D. Don't worry about those. I want you to just consider the RNS. That's what we learned. So if you put a mirror here, this should be your image. The opposite of the R chiral center is definitely S, and if you doubt, do the assignment again. You will see that you have 1, 2, 3. This time you're going R, the smallest group is towards you. It needs to be a way to assign true chirality, switches to an S. So these two guys are enantiomers. They are enantiomers, so they are enantiomeric forms of the glyceraldehyde. Okay? So without showing the wages, this is how this structure will look like, and this is how this structure will look like. We usually don't show the wages in Fischer projections because we assume you know that anything that's horizontal must have the toward shaded wedge. Another stereochemistry that you can talk about other than the R and S stereochemistry, one can define the Fischer projections as D, or the sugars as D and L, where D corresponds to R and L corresponds to S. But the shortcut is this. Look at the tail of the Fischer projection, okay? That's the tail of this trios. So focus on the OH. So when the OH is on the right side, when the OH next to the tail, because we read or number this Fischer going downwards, this is the tail part, okay? When the OH is on the right side, that's considered a D. So this is D glyceraldehyde, what would have been an R, okay? And then if the OH next to the tail of the Fischer projection is on the left side of the Fischer projection, then we call that an L, glyceraldehyde. So it's common for you in the market to see D and L rather than R and S. That's what D and L means in sugars. So OH on the right, you get a D. Okay. OH on the left, you get an L sugar, and gonna be tested on this in the final. Okay, the chain can be longer, but like I said, all you need to do is to look for the second last carbon. Okay, second last carbon, or the carbon next to the tail of the Fischer. I call it a tail because we read Fischer projection downwards. This is the OH you consider is to the right, so that's a D. This is the OH you consider is to the left, that's an L. Of course, these two guys are aldoses because they contain the aldehyde. Okay, same happens with ketosis, because now you have a ketone. Read your Fischer projection downwards, look at your second last carbon. Okay, that's gonna be next to your tail of the Fischer, so it's to the right, so that's a D ketose because you have a ketone right there. This one's to the left, so it's an L ketose because you have a ketone right there. Okay. And it gets crazier because there are so many other forms of Fischer projections you can get out of carbohydrates. So let's define some more stereochemistry. Again, you don't need to memorize, you just need to identify whether it's a D or an L, okay, or an R or an S, because we did that before, or whether it's an aldose or a ketose. That's the goal. So you start with the triose. In this case, we're choosing to start with the D triose, specifically glyceraldehyde. Again, you learn that in biochemistry when time comes, those who have to take biochem. So, like I said, don't worry about the positive and negatives because those ones would have been defined by the polarimeter, the instrument. But if you have 3 carbons, so 1, 2, 3, like I said, we read going downwards. The OH is on the right, so this has to be a D. It's a triose because you have 3 carbons. Add 1 CHOH. Now you have a tetrose. Add an extra CHOH, you have a pentose. Add an extra CHOH, you have an hexose. Now you know how those names came by. So now let's go to specifics. The CHOH that's added could have the OH on the right or to the left. Now the rest, this stereocenter is kept, this stereocenter is kept. Only this one is switched. Okay, by eyeball you can see that stereocenter is switched. So if it was an R, it's turned to an S, but the rest stays. So the relationship between these two guys is what? Where one stereocenter is kept, the other one is switched. This is kept, this is switched. So, I mean, you see this is drawn the exact same way. So the stereochemistry there is kept. Okay, and I think in this case the stereochemistry there is what? Let me quickly define it. And yeah, that's an R, so this has to be an R. And then here 1, 2, 3. So I'm going 1, 2, 3. You can do this for your practice. So this is an R right here. 1, 2, 3, 1, 2, 3. And this is an S. So if you are to compare, you have RR on this structure and SR on that structure. So you see again, the bottom stereocenter is kept, the top one is switched. So these two guys are the stereomers. So even without assigning R and S, you can eyeball and see. All right, away from that, so definitely these guys are also the stereomers. You would be tested on that because again these stereocenters are kept, these are kept, and this is switched. Okay, anyway, they are still D pentoses, specifically ribose for this one because the OH is on the right. The OH is on the right, is still a D, but that's called a ribose. This is called arabinose. Okay, now even though I'm calling them the stereomers, looking at this molecule, I think this one is kept, the stereochemistry there is kept, but now these two are switched. Okay, this stereochemistry is switched. They're still the stereomers. Okay, and they're still D's because the OH on the tail, next to the tail, is on the right side. Okay, so you have xylose, you have lysose for these two guys, and then you have, okay, add one more carbon. These two are still diastereomers because this stereocenter is switched. That's called allose, is still a D. That's on the right, on the right, on the right. All these are D's because the OH next to the tail are on the right. If they're on the left, it would have been L. Okay, but they're D's. So you have allose, maltose, glucose. This is what you guys are very much familiar with. So this is D glucose, this is L glucose, and so forth. There's mannose, glucose, idose, galactose. That's another common one. And then talose. You don't need to memorize these structures. Okay. All I need you again to know is whether it's a D or an L, or whether it's a ketose, an aldose, or whether the two structures are enantiomers or diastereomers, whether it's a triose, tetrose, pentose, hexose. Okay. Epimers are subclass of diastereomers common in carbohydrates. They are related to one another by having a single stereocenter of opposite configuration. Okay, that's ribose and arabinose are epimers, but diastereomers to xylose and lysose. So as you can see, these stereochemistry are the same, but they are switched here. Okay, they are switched there. So these two structures are epimers. It's still correct to call them diastereomers. We're just using a specific word, epimers, because you're considering sugars. Same thing with these two guys. They are epimers. So ribose and arabinose are epimers. These two are epimers. These two are epimers. They differ in only one single point in configuration. Okay, so in chapter 9 we said that aldehydes and ketones can be attacked by a nucleophile, and if the nucleophile is not water, if the nucleophile is an alcohol, you either make hemiacetal or you make acetase. So if you have an aldehyde or a ketone, the carbonyl can be attacked by intermolecular reaction to make hemiacetal, okay, which is the most stable and dominant form of monosaccharides, which means you want to form rings. So instead of them staying as straight chains, they usually close up, just like if you have a snake and the snake eats up its tail, what you end up with is a ring. Okay, you end up with a ring. So the ring of the sugars are more stable than the Fischer projections. Okay, and that happens by just doing a nucleophilic attack with the alcohol. So let's look at that. So these are Fischer projections. So these are Fischer projections. I want to explain this slide of cyclization using a mechanism. Okay, so the Fischer projection would cyclize. It's like a tail attacking the head. So which OH do we use to make a hemiacetal? Again, it's gonna be the OH that you're trying to classify as D and L. That's gonna be used, that OH. So you can imagine if this OH attacks the carbonyl of the aldehyde or the ketone. In this case, it's an aldehyde. This is an aldose. If you attack that carbon, this opens up. So basically, what you're doing, you're making a 6-membered ring. Okay, so we're going to cyclize the Fischer projections. So let's number our carbons here and see. From top is 1, 2, 3, 4, 5, and 6. Okay, so we will use the oxygen next to the last carbon as a nucleophile to attack carbon 1, which is a carbonyl. So imagine this attacking the carbon, and this opens up, the carbon opens up. It opens up picking up a proton, which could be probably this proton, because if you look after cyclization, that proton is missing, this hydrogen is missing, it was taken out. Okay, so once this opens up, okay, it gives you an OH. See, carbon 1, it gives you an OH. This hydrogen right there, right here is this hydrogen right there. Okay, so the proton picked up by the blue oxygen could be this. Okay, and for clarity, that's the blue oxygen, that's the blue hydrogen, that's carbon number 1. I think that's clearer. So now you see carbon number 6 is not part of the ring. If you are wondering how the 6-membered ring came by, let me number like this. So call that 1, 2, 3, 4, 5, 6. This time I'm just numbering the elements of the 6-membered ring. So you see there's 6. So this green numbering could be 1, 2, 3, 4, 5, 6. The green numbering is just numbering the member of the 6-membered ring. The red numbering is what was numbered here in black. It numbered the carbons going down. So you see, you made an OH. Okay, there's this OH and there's an oxygen. So we said whenever a carbon has OC and has OH, we called that molecule hemiacetal, because you have an OR group. This is the OR group. The rest of the chain is a OR group and an OH. So the OR group and OH sharing the same carbon, that's hemiacetal. So that's the hemiacetal structure of glucose. You started with glucose, Fischer, now it's a glucose in a ring. So because it's a 6-membered ring, we usually call this pyranose. If it was a 5-membered ring, we call it furanose. Okay, so again, that's your Fisher projection. You could draw it with wedges and then rotate. You turn it 90 degrees. So let's say you are turning it 90 degrees that way. You get this straight chain, and then now it's gonna be this this oxygen. Let's see, yeah, it's gonna be that oxygen attacking the aldehyde. So before it does that, let's kind of allow this straight chain to curve, right? Like curve it. So you're gonna end up with this structure, and now you're ready for this to attack, but you want it to be very close to the aldehyde. So we do a rotation here. Okay, you do a rotation here. Now the OH is next to the aldehyde. You see, now if it tries to attack at this point, it's too far away. So we do the rotation. As we do the rotation, this hydrogen goes down. Okay, and then the OH goes on the other side, close to the aldehyde. Now you can use the lone pair to attack the carbonyl of the aldehyde, and this opens up. It opens up, picking up proton. So at this point, this is what I was trying to explain here. All right, so this is my explanation right here. I was just trying to use a shortcut to help you quickly see. So the reason why we are doing all this rotation, because is you have to define which groups end up down, which ends up up. So by default we usually say that groups that are on the right should end up down the ring. So you see what I've circled here should be down. OH is down. The OH is down on the carbon 2 in red. So the H on carbon 3 is on the right, so it's down. The OH on carbon 4 is on the right, so it's down. Okay. Now this one in blue is gonna be switched. So even though it's on the left, it's gonna be considered as if it's on the right, so it should end up down. Why does it switch? Because we did the rotation on here. So that's why this one switches. These two guys, this oxygen was used to attack, so it's this one after rotation, but my focus is this hydrogen. It's to the left one, we think it should end up up, but because we did the rotation, it should end up down. Okay, now these ones are on the left, so they should end up of the ring. So you'll see the hydrogen on carbon 1 on carbon 2 is up, OH on carbon 3 is up, H on carbon 4 is up. Okay, so now what about the CH2OH? Because of the rotation, and we know the OH, the oxygen of the DOH is one that did the attack, is on the structure of the ring, so this CH2OH should be up. Okay, why? Because we already know that this H on the left should have been up, but it's down, so the CH2 has no option but to be up on the ring. Okay, those are very technical things to do. I don't think I'll be testing you to draw the mechanism or predict the chirality in the test, but I do want you to see that yes, Fisher projections can be converted to hemiacetars, which are rings. So glucose that's on Fisher can be converted to glucose on a chair. Okay, so you can get chairs, and the same chair can be drawn in what we call Howard projection, where we just draw the fabric of the chair, the skeleton of the chair on the plane. Okay, so the Howard projections look flattened, but again, this looks like a chair and is the best representation on how the molecules will be. So you might end up with anomers. Anomers is just where there's a difference in stereochemistry on one point of the ring. So you see how you are we attacked here. We attacked the carbonyl. You can attack from the top, which means the OH will be at the bottom, or you can attack from the bottom, which means OH will be on the top. So you're gonna end up either with the OH on top, on the same side as the CH2OH, we call that beta, or you'll end up with the OH at the bottom. So let's say the CH2OH and the OH are opposites. Okay, so I'm just trying to use the Howard. I will not draw what's on this one. My focus is on this. So if this OH and the CH2OH are opposite, we call that alpha anomer. Where the OH and CH2OH are on the same, we call that beta anomer. So I'll test you on that too. I'll ask you to classify the rings as alpha or beta. So you see here CH2OH and OH are on the same. That's beta, and with this carbon bearing the OH is called the anomeric carbon because this OH on that carbon could either be down or up. So where the OH is down, opposite to the CH2OH, on the anomeric carbon, the carbon where you can switch stereochemistry, you call that ring alpha. So this is alpha glucose and this is beta glucose. Very important for biochemistry. Okay, again, where you have the stereochemistry, the new stereocenter, we call that an anomeric carbon, where you can create alpha or beta. So remember again, CH2OH and OH opposite. These two guys across the oxygen, you get alpha. CH2OH and OH across the oxygen on the same side, you get the beta anomer. Okay, we'll continue from there.